Okay, so we have been setting up the scene to discuss a very important theorem, namely the Cauchy theorem. And in this lecture, we will look at how the Cauchy theorem comes about and also look at some of its consequences. Okay, so the Cauchy theorem is fairly straightforward to state. So if f of z is analytic in some closed region and f prime of z is continuous in R, right? So and let C be a simple closed contour in R, right? So then this contour integral f of z dz is equal to 0, right? So what is meant by a simple closed contour? So it's a contour which does not cross with itself, and nothing very complicated about it. It's just as simple as it gets. It's a contour which comes back to its own starting point and without crossing at any point. And this entire C must lie within your domain, right? It's a closed region R. Now this is the Cauchy theorem, which we can actually prove, right? So it's quite straightforward to prove when we have these conditions in which which this goes by the name of Cauchy's theorem. And there's a slightly modified version which we'll also discuss later on, and that has a slightly different name as well. So since f of z is analytic in the entire region of interest, we can write its derivative at all these points, right? So first of all, expanding f of z in terms of the real part and the imaginary part, so u of x comma y plus I times u of x comma y, we have f prime of z is dou u by dou x plus I times dou v by dou x, which is equivalently, which can be written, because you have Cauchy-Riemann conditions which hold, as minus I times dou u by dou y plus dou v by dou y, right? So so in place of dou v by dou x we can put minus dou u by dou y, and in place of dou u by dou x we can put dou v by dou y. So this is just a direct consequence of Cauchy-Riemann conditions. Now if we write out the contour integral in terms of the real and imaginary parts of this function f of z, we have this contour integral f of z dz is equal to contour integral over c u of x comma y dx minus v of x comma y dy. So this is like the real part, plus I times this another contour integral over the same contour, but now you have v of x comma y dx plus u of x comma y dy. And this is where the Green's theorem comes in, right? So the analyticity of f of z guarantees that both u of x comma y and v of x comma y are both continuous in R, and moreover f prime of z is also continuous in the entire region, right? So this is also part of the conditions which we put into the theorem, and therefore the first order derivatives of both u of x comma y and v of x comma y themselves are continuous in R. So all the conditions which are necessary for Green's theorem hold, and then we just simply apply Green's theorem. So invoking Green's theorem, we see that each of these contour integrals on the right hand side above can be written as double integrals in the region of interest over R. So now you have the first of these becomes minus dou v by dou x minus dou u by dou y dx dy. Then you have plus I times another double integral dou u by dou x minus dou v by dou y dx dy, right? So but a little bit of thought reveals that in fact both of these terms will just go to 0, because in fact this is nothing but, it looks like the Cauchy-Riemann conditions, right? So it's like the two terms in one of the Cauchy-Riemann conditions, which says that dou u by dou y must be equal to minus dou v by dou x. So therefore these together is just 0, and again dou u by dou x must be equal to dou v by dou y. So since Cauchy-Riemann conditions hold in this entire region, at every point this holds, so at every point this is 0, and so you're doing a double integral of basically 0 over some region, so it's just going to be 0, and therefore immediately we see that the Cauchy theorem holds. So it turns out that all these conditions involving f prime being continuous and all this is actually a little redundant, and so that's what the statement of the Cauchy-Goursat theorem is, right? So that's simply states that if f of z is analytic within and on some simple closed contour C, then that's already sufficient for this result, right? So the key point is that your function f of z must be analytic everywhere inside this region, and your closed contour C itself is a simple closed contour C, and that's it. And so a closed contour integral of this kind of z dz is going to be 0. So let's look at a few examples how this plays out. So if you look at this integral, right, so this we have already seen. So if you take an integral, closed integral of the function z to the n dz, where n is a positive integer over closed contours around the origin, right, so this is going to be 0, right. So consider a circular path of radius r centered around the origin, and you just put z equal to r times e to the I theta, so dz is equal to r times e to the I theta times I d theta, and the contour integral is just given by this. You expand it, in place of z to the n you write r times e to the I theta the whole power n. You have r e to the I theta I d theta, expand everything nicely, and then theta goes from 0 to 2 pi. So there are no difficulties, it just goes through, right. So this is a calculation you're familiar with, and finally we get r I times r to the n plus 1 with e to the I times n plus 1 theta divided by I times n plus 1, and to be evaluated at 0 and 2 pi. At both of these points it's going to be the same, and you get 0, right. So there is no which is because n is a positive integer, you get the same value at the ends. And so this is consistent with the Cauchy theorem. We need not have done any of this calculation, because after all, z to the n, where n is a positive integer, is an entire function. So everywhere in the finite complex plane, z to the n is analytic. So if you believe the Cauchy theorem, then automatically, without doing any calculation, we should be able to say that this contour integral is in fact 0. Right? But we have also explicitly checked this using this calculation. Let's look at another example. So suppose we consider something like z to the 1/2, right? In place of z to the n, suppose I look at z to the half. Now we have to be, a bit more careful. First of all, z to the half is a multi-valued function, so you have to specify the branch that you're working in, and specify the branch cut. So now suppose we restrict the polar angle to lie between minus pi and plus pi. Right, so this is the principal branch, considering a circular path of radius r. Again, just like in the previous example, now again z is equal to r times e to the I theta, from which we can write dz is r times e to the I theta times I times d theta. Now the contour integral is given by this expression minus pi to plus pi, right, because that's the restriction on the polar angle that we have put. And then we go from r e to the I theta the whole power half. You can carefully collect these terms. You get r to the half e to the I theta by 2 times r times e to the I theta I d theta. So you can pull out I times r to the 3 halves. Then you're left with just this integral minus pi to plus pi e to the I theta 3 by 2 theta d theta. And so if you carefully evaluate it, so the answer is going to be just minus 4 by 3 times I times r to the 3 halves. So we see that indeed this answer is not 0, right? First of all, it's not 0, and also it is dependent on r, right? So it's a path dependent quantity, right? And it's also it depends on the size of the circle, right? And so if you think about this, why did this happen? So the reason this happens is because this function z to the half is not analytic in the entire region under consideration, right? So Cauchy-Goursat theorem does not quite hold for this type of a contour integral, because z to the half there's a branch cut sitting on the negative real axis, and therefore there is no analyticity at that point, and therefore there is no way for this kind of a this contour integral to satisfy the conditions essential for the Cauchy-Goursat theorem to hold, and therefore indeed this contour integral is not going to be 0. So in fact, the value of this contour integral will depend on the branch in which you are working, right? So if you have chosen a different branch cut, right, and a different branch, so suppose you have chosen the positive real axis to be the branch cut. In this case, we would restrict the polar angle to lie between 0 and 2 pi, and then the answer would be, you can check this, will turn out to be minus 4 by 3 r to the 3 halves, right? So I mean, the fact that this depends on the branch you're working on is not a surprise, right? So this is a consequence of the fact that your integrand itself is a multi-valued function, right? So given a certain value of z, you will ascribe some value to this point z to the half, right? Since there are many different values, so in this case there are two different values. So in general, if you have a multi-valued function given a point z, if there are different values you can ascribe to it, depending upon which branch you're in, this kind of a contour will certainly give you different answers. So it's not a surprise. So you have to pick your branch and pick your branch cut. And once you have picked your branch cut, if you want the conditions required by Cauchy-Goursat theorem to hold, then you must ensure that your contour does not cross the branch cut, right? So there are two aspects to this. One is, of course, the choice of the branch, because you're working with a multi-valued function, and then the contour in question. So the contour is not allowed to cross the branch cut if you want analyticity, right? And so in this case, since it does cross, you get an answer which is not zero, and after all there is no contradiction with respect to the Cauchy-Goursat theorem. So let's look at one more example. So in fact, we can work out this general result. So instead of considering z to the z to the half, we can actually look at z to the a and do this kind of a similar contour integral where a is any non-zero real number, right? So if we use the principal branch, so we have seen how such a function f of z can be really thought of as z to the a, which is e to the a times log z. And if you work in the principal branch of the log function, which corresponds to the principal branch of the argument function, so then you restrict mod z to be greater than 0, and you restrict argument of z to lie between minus pi and plus pi. So again, we have taken the negative real axis to be the branch cut. So now if we consider a circular path of radius r centered around the origin, so once again, these things are standard. Z is equal to r times e to the I theta, and dz is r times e to the I theta I d theta. So the contour integral is z to the a dz. So you do this contour integral, carefully collect all these terms, z times r times e to the I theta the whole power a, then it becomes r to the a times r, which is r to the a plus 1. There's also an I which comes out, which comes from this d theta. Then you're left with this integral e to the I times a plus 1 times theta. D theta needs to go from minus pi to plus pi. So then this is nothing but I times r to the a plus 1 is just something which you pull out. Then you have to evaluate this quantity e to the I times a plus 1 theta divided by I times a plus 1 between plus pi and minus pi, right? And you can write down the answer as 2 times I times r to the a plus 1 divided by a plus 1 times sine of a plus 1 times pi, right? So some thought reveals that if a is any integer other than minus 1, then immediately we see that this contour integral actually vanishes, right? So in other words, we have this result, contour integral of z to the n minus 1 dz is 0 for any integer which is not 0, right? So I have shifted this, so instead of z to the a, I have taken it to be z to the n minus 1, and then if n is either plus or minus 1, plus or minus 2, for all integer values other than 0, so this integral is 0. So this is this fact is of great importance, and we'll return to this later on. But it is worth emphasizing right away that this is a the fact that this quantity is 0 can be extracted from the Cauchy theorem for positive values of n, but for negative values of n, you cannot use the Cauchy theorem, right? So the reason is because for negative values of negative integer values of n, you have a singularity sitting at the origin. So you would have something like 1 over z squared or 1 over z cubed and so on, and then it's a problem. You cannot blindly apply Cauchy theorem, but still this integral, this contour integral, is actually 0, right? So this is something that we have worked out from first principles here, but we also saw this from the antiderivative perspective as well, right? So, but when a is equal to minus 1, that's very special. We also worked out that particular integral, breaking down the contour into two different parts. But here we see that, using this general approach, we can we can use an approach similar to this, starting with a equal to -1, and then we write, in place of 1 over z, we write 1 over r times e to the I theta, then dz becomes r times e to the I theta times I times d theta. So this r times e to the I theta actually just cancels, and then you're left with just I d theta, and so you get 2 pi I, right? So this is also a valid way of approaching this problem. And so indeed, this is the same answer which we also found by taking this approach where we wrote down the antiderivative and worked out c1 and c2 different portions of your contour integral, and then the final answer is 2 pi I. So these results of the contour integral of the function z to the n minus 1 dz being 0 for all integer values, positive and negative but not 0, and also the fact that the contour integral of 1 over z dz, where the contour goes is encloses the origin, is 2 pi I. These are results of great importance, and so they have applications which we will return to at a later time, right? So but as far as this lecture is concerned, we looked at the Cauchy theorem, the conditions which go into it, and how there is a version of the Cauchy theorem which is called the Cauchy-Goursat theorem, where the conditions are not as restrictive, and how to make use of some of these. We also looked at some applications of the Cauchy theorem and how one has to be careful and how one cannot blindly apply it. One has to check the conditions carefully. So that's all for this lecture. Thank you.